No, okay, let us resume. So, we overviewed what we actually told already last week, but I hope it was useful to make the second iteration. So let me also write it in English. So it's examples of non-countable sets.
А вы не включили демонстрацию?
Ага. Да. Нормально сейчас, да?
Да.
Okay, so we revised again the idea of how sets are compared in size, right? Via one-to-one correspondence. Then we introduced the concept of countable sets. So countable is a set which is in one-to-one correspondence with set of natural numbers, or it is the same cardinality, and also put it that way. So there are different expressions, but the same idea. So two sets are the same cardinality if there exists one-to-one correspondence between them. And actually, we proved about certain sets they are countable by describing such one-to-one correspondence with set of natural numbers. Then also recall that actually I didn't tell it last week, but it was important amendment. Today, we also introduced a way to talk about sets of being higher cardinality or lower cardinality, right? This is via this theorem that I did prove, however, just announced it. So we should keep it in mind that all sets are actually comparable in that way. And now, yes, we come to example of non-countable sets. If all sets would be countable, all this theory would be somewhat trivial, not interesting, right? So our examples, recall again, last week, I'm not going to repeat everything I told last week because you can also go back to recording and look at again. So our basic example was this interval of real numbers between 1 and 0. I can also picture it actually. Yeah, sorry, I stopped video. Stop my video, otherwise I cannot really. Yeah, so make another attempt. Yeah, that works better. So we have this real line, so-called, right? I think you're familiar from school. So we have 0 somewhere and 1. Let me put it in some reasonable distance. And now we are interested actually in the set of all real numbers, not all real numbers, not really all, but within that interval. But that was actually a technical thing that actually includes 0 and includes 1. So it's a sort of interval. I can put that kind of brackets here just to show that we include ends, both ends of this segment, right? Yeah, otherwise, probably I can call it 1 prime, right? Because 1 prime is just set of points in that interval, right? Set of points. And points within, I would say, right, within including endpoints, within this interval. And I just recall you, if you forgot, that actually intuitive notion of real numbers, it's just a point of the line. So every point corresponds to certain real number, but then we needed all the theories that actually we started today with recalling these definitions of real numbers, but they only needed because just saying it's a point, it's theoretically not sufficient. Even intuitively, it's, of course, it's probably most appealing. So you really need to combine this geometrical intuition with this theoretical constructions like Cauchy sequences or Dedekind cuts, right? So it's important in mathematics to keep this intuitive side and theoretical side and somehow combine them together. It's actually very general moral. That's how mathematics basically works. Okay, so yeah, it's basically the same set or it's different set. You see, it's not really important whether we saying points and the real numbers are the same objects or different objects. That really doesn't matter for that issue concerning size, concerning cardinality, right? And then actually we introduced some other description, and just recall we used binary fractions. Remember binary fractions and why we needed binary fractions. So it's a fraction, but in binary system, in binary notation, where we have only two symbols, 0 and 1, and we spent some time by showing that actually we can represent not any number actually, but many numbers in that way. And since we want really to represent all real numbers, we should not consider only finite strings of this 0, 1, right? But also infinite. It's similar as, I remind again, that's example if we have this number pi, which is actually a transcendent number. It is a real number, it's not rational, and we may get more and more and more digits in this expansion. And similarly, we do with just 0 and 1 instead of decimal. Positional system, we use binary. And so every point or every number within that interval, which is a fraction, right? So the only numbers which are not fractions are 0 and 1. So everything which is between 0 and 1 is a fraction. And we somehow may forget about this first 0 and then only look on this tail, which is some infinite sequence of 0 and 1, right? And this is already follows actually from our theory of Cauchy sequences, that each such infinite sequence corresponds to certain real number or point, if you like, and the other way around. For every point, we may construct a corresponding infinite 0-1 series, right? So that was a second example, but actually representation. What I just said about that every point or every real numbers allows for such a representation basically establishes one-to-one correspondence, right? For each point, it's individual expansion, and for every such expansion, individual point. Okay, so if you like, you may think about this as a one-to-one correspondent, but it's important now we actually we are talking about set of all such sequences. This is important, right? Not only one sequence, not some, but all of them. So set of all underline this, all 0, 1 sequences. Okay. Yeah, so that was the second way to describe basically, as I say, the same example. And the third one, which I think I also mentioned last week, but let us, that will be more important in what follows. It's this, that actually observe that each such sequence corresponds to certain subset of set of natural numbers. How? No, very simple. If I just put natural numbers, say here, right? Just the position number, the number of position, and then I making the following convention. So I form my subset P, which is a subset of natural numbers, right? In the following way. So if I have 0, I don't take this number into my subset. If I have 1, I do, right? And so to each such 0, 1 sequence corresponds exactly one subset, right? So if I now talk about set of all 0, 1 sequences, is actually set of all subsets. It's actually the right word is equipolant. I don't want to give you too much of terminology, but equipolant, it means the same size. The same size, the same cardinality, it's all the same. So this is what we denoted this way, that M, N, right? That there is one-to-one correspondence, right? So I can also describe the set as set of all subsets of N, right? So let me write set of all subsets of N, of set N, right? And there is also in English, but not in Russian, to the best of my knowledge, there is a special name. It's called also power set. You see, here there is a, in Russian, cardinality we call мощность, right? But this power set is not, it's not the same, you see, so power set. So power set is just set of all subset of given set. So we're taking our set, say N, set of all natural numbers, right? It consider all subsets. As I just said, it's actually, it's equivalent to set of all 0, 1 sequences. And now, no, okay, I will not give you again the full proof. Remember, we did this proof with this diagonal method, but I think I really encourage and even, I would say, urge you to look recording and this whiteboard recording of last week, just to see how it works. I don't want to repeat because it takes some time, right? However, we proved. No, I may only remind you how it worked, right? So it was proved by reductio ad absurdum. So we assumed that we could somehow list all these sequences in one big list, and then we constructed a sequence which provably was not in that list, right? It was so-called diagonal argument or diagonal procedure, which is actually very important. Or diagonal proof, sometimes it's called diagonal proof, right? And that actually proved that it couldn't be done, right? That this hypothesis that we can actually list, and list something means establishing one-to-one correspondence with natural numbers, right? Because in anything we call a list, there is first element of the list, second element, and the kth element of the list, and so forth, right? So we're saying we can list certain set, present it as a list. It's the same or less that we enumerate it, so it's countable, right? And we proved that if we assume this hypothesis that we somehow manage to list it, then we can present a new sequence that is probably not in that list. And that proves that's actually this set is not countable, right? And looking here on this number 3, we can also say that this operation, we can think about this P as operation of, we have a set, and then we consider the set of its subsets, right? This power set operation. And so this power set operation rises cardinality. So, right, it's the only operation that we actually came across so far that allows to produce something really bigger, right, in this set theoretic sense. All right, and actually, if we have some time and courage, I will prove you a generalized version of Cantor theorem, right? Because so far we only proved it for n. However, I can only announce it now, right? So it's called, you can also Google it, generalized Cantor theorem, Cantor for your Cantor. Okay? And it says that for any given any set M, the size or cardinality of power set of M, right? You can write it that way, is strictly bigger than cardinality of M. So that is something that really rises cardinality, it rises size, and it not only for countable sets, it works not only for countable but also for uncountable. So actually, we can rise power further, rise size further and further. Yeah, and we may actually give a proof. It's not very complicated. It's actually interesting. This proof of the generalized theorem. However, I should say that in kind of practical mathematics, we only work with that two sizes, with sets of that two sizes, right? And one of which is just countable set like n, or as we've seen, it's also the size of, say, integers or rationals. All right, it's all the same size, and size of kind of next size, which it corresponds to size of R, right? No, we didn't prove yet, and we'll look into it maybe a bit later, that actually it's, say, we are not taking interval, but just the whole line, it will be still the same size, right? And that's other size, sometimes it's written that way. It's 2 power n that way, right? And this is because we just review it in final case, right? That if you have set of 5 elements, then its power set, right? Number of its subsets is 2 to 5, right? Which was 32 that we just recalled. You can look in some previous pages, and by, say, analogy, if you like, that is extended to this infinite situation. And so we can say that this is strictly bigger than a size of n. Yeah, probably I should put n here, so that way, okay? Yeah. No, the only thing it's rather for, how say, general cultural background. I think since we are talking about these things, right, I may mention just one thing, which is called Continuum Hypothesis. But don't tell anyone you study in your course Continuum Hypothesis, because people would say it's too abstract, too complicated mathematics, but still. So continuum hypothesis is concerned with the following question. So we have now, say, n, that size of n, right? So it's countable sets or any other countable sets. And we have this size of power set of n. Ну, давайте все-таки русское замечание, что по-русски это называется множество мощности континуума. In English, that expression is not used as far as I know, but yeah, but people still talk about continuum, right? Continuum means, do you know this word? It's Latin word, but do you understand continuum, what continuum is?
Ну, это как законченный.
Нет, это как непрерывный. Ну, по-русски тоже так говорят, continuum. Но это от слова, ну, you know English verb to continue, right? To continue. To continue. Вот, это законченный будет как-то complete, что-нибудь такое. Нет. To continue, there is, как сказать, what is adjective for continual? Oh. Yeah, so let me just look, because I think I'm somehow getting tired, and again, I have some linguistic concerns. So, continuous, of course, right? So we have a word continuous, right? По-русски непрерывный. Continuous, непрерывный. For example, continuous transformation, that is important geometrical concept in modern mathematics. Continuous. So continuum is something continuous, and so it's called continuum, or по-русски мощности континуума, because of this line that we had. We kind of okay, it's not important, observed many times, right? So again, if we think about these real numbers as points, that's where this idea of continuum comes from. Of course, there is more than just the size, right? These points should somehow fit each other to form this continuum. That is clear, of course. However, if you like this effect of rising cardinality, it has something to do with this geometrical property, right? By the way, I think I also should mention that since we proved that the set of real numbers, say between 0 and 1, is not countable, right? And actually, now we can say something more precise. It's not only not countable, but it has this cardinality, which corresponds to cardinality of all subsets, natural numbers, right? And remember, we, for example, proved the fact that square root of 2 is not rational, right? So we ask whether or not, if we put all rational numbers, there are any like holes. And we proved that there are such like empty points, right? By showing that, for example, point that corresponds to square root of 2 is not rational. That was the very beginning of our course, right? But now, if you like, we have a kind of indirect justification of this, because we know that set of rational number is countable, and that means exactly that set there are more points than any countable set. Yeah. No, actual situation is a bit more complicated, because I mentioned you also algebraic numbers. We are not going to explore this, but those are numbers including square root of 2, which are roots of all, say, polynomials with rational coefficients, or say solution of all equations you can imagine. And that's actually turns out to be also countable. Yeah, I will not give a proof. It's not very complicated, but still. But then remember, there were also transcendental numbers, so called like pi, right, which cannot be represented as roots of some polynomials. And again, you see different different theories fit together nicely so far, and that's good, of course, right? If we would prove in different ways some things which are somehow not compatible, we can get even formal contradictions. That would mean that something goes really wrong. But now, so far, there is, say, evidence that things go reasonably well, right? So we know that there is much more points, so to speak, than any countable sets, and we know some of these points. Of course, we cannot really tell much more. Okay, but now I go back to this continuum hypothesis. So the continuum hypothesis is related to the following question. So what we proved is this, right? But question is there anything in the middle, right? Is there any set, or say class of sets, which have size which is strictly bigger than natural numbers, right, which are also uncountable, but which is strictly less than this cardinality that we obtain, right, that cardinality of continuum? Is there something in the middle? And Georg Cantor conjectured, put a hypothesis that no, that there is no such a thing, right? No. No such intermediate size. Yeah, and then he tried to prove it. At a certain point, he believed he proved, but then other people found kind of failures, and that's a rather complicated story. So some people believe that's a problem that simply cannot be settled. So basically, you can hypothesize one version of the other, and you get kind of different set theories. That's one view. However, there are, say, also very serious people, experts in set theory, which believes that the problem is still open, right? They are, I would say, minority, but still it's very, serious viewpoint. So some people still believe that the problem is simply open and we simply don't know, and they hope to get an answer. So that's again example of open mathematical problems. There are many of these, but that is also kind of foundational. You see, it concerns very foundation of mathematics. Yeah, but that's again, if you want to study that serious, you should really study set theory, and it becomes kind of special business, because if we're talking about set theory as foundation mathematics in kind of practical sense, right, then actually continuum hypothesis doesn't matter, because we only use. But what does matter is understanding that that cardinality of n, right, is less than cardinality of continuum. That's important in many applications, in calculus, differential integral calculus, in many fields. This is somehow important, these issues of cardinality. Yeah. So I think yeah, probably before I go to next topic, let's us try to make some small exercises, okay? Let's do some small exercises, which I think otherwise if I just tell you about things, right? So yeah, I'll give you also test that's from my last year. So let's look. And I had such problems, some such questions on the exam also. So I just ask you to give me answer, yes or no answer. And of course, as always in mathematics, some proof and justification, whether or not two given sets, and I'll give you the sets, have the same cardinality, or they're the same size or not the same size. Right. The set of positive even numbers and the set of positive numbers divisible by 3. Yeah, that's. So what do you think? No, even numbers we discussed, right? And so we know they are countable. But what about not even numbers, but those divisible by 3? So it's we don't have special word for that, but it's kind of similar, right? So even divisible by 2, and now I want to consider numbers divisible by 3. No, look, how to answer that sort of questions, right? No, of course, I may accept that if you refer to some, say, established facts about continuum, so I don't want every time you making this diagonal argument. However, very generally, in order to prove that two sets are the same cardinality, the same size, right, you should describe one-to-one correspondence. This is sufficient. Now, in order to prove that they are not the same size, it's actually more difficult, almost in all cases, because in that case, you should prove that no such correspondence exists. And that's more difficult, right? However, in that case, in the second case, you may refer to some known facts, so to speak, right? That cardinality of continuum is higher than cardinality of countable set. Okay, let me do this. So I do, or some of you want to try?
No, do it, please.
No, okay, no, okay. I'll do it in a kind of naive way. So what are even numbers? 2, 4, 6, 8, etc. So I may say 2k, right? Where k is actually 1, 2, 3, 4, k, right? And what is divisible by 3? It's what is 3. I start with 3. Next goes 6, right? Next goes 9, etc. So it's 3 times k, right? And you see, again, it's kind of straightforward, right? So here we had correspondence that k and 2k, which actually works both ways, because every number here even has this form. It's divisible by k, and now I have again that's kind of two-way correspondence to k to 3k, right? And actually here it's something which pretty obvious. We didn't prove it. It can be an exercise for next week maybe. However, if both of these sets are countable, right? This set is countable and that set is countable. So they are, of course, the same size, right? So you see there exists also one-to-one correspondence between these. So how you, well, basically here you should multiply by 3, 2 or divide by 3, 2, right? So so if I have this set, I call it E, right, even, and here I have let me use the same letter. It's not even, and I put the 3 somewhere, right? Just notation. Yeah, here it is. And here is my E. And here, yeah, and here is my N. Right. So here I multiply, and then to go back, I divide, or say I multiply by 2/3. Yeah, so it also works. So of course the answer is positive. They are the same cardinality. They both countable, and that's how I establish one-to-one correspondence between them. That's the first exercise. Let's now look second exercise. The same question, but now I give the set of real numbers of, oh, okay, that time I say open interval. So I exclude this 0 and 1. I exclude the endpoints, and the power set of set that just consists of 2 elements, 0 and 1. So what do you think? Now, even give me answer some, say, informal argument. I don't really, now, you don't have really very, how say, formal setting to require kind of formal proof. So I rather want you give some informal argument, but reasonable. Okay. So this is 0, 1, that is just 2 elements. You see, remember we use this figure brackets or parentheses, how it's called, just for listing elements. So this is a finite set, but now I should look at its power set, right? And then it's on the one hand, and on the other hand, I have this open interval. So what do you think? Okay, what is power set of 0, 1? Of course, I could call it A and B here, right? It's not important. Just 2 elements, a set of 2 elements. How much elements is its power set? So what is the size? How many subsets in that set of 0, 1? Well, you already gave me correct answer several times today. I think in our example it was 5 elements, and now just 2 elements. Why it's more? It's just a little bit different length. Probably I didn't use this word power set, but it's just set of all subsets. So how many subsets? And if I say A and B instead of, it would be better, no? Because you should understand that that is equivalent. So it's not important that it's only size that now matters, you see? And size is just 2 elements. So how many subsets?
4.
Yes, right. Just 4, right? So that was one set we had to consider, and the other set was a set of all points on between 0 and 1. Now 0 and 1 are real 0 and 1, they are real numbers, right? But now I put it that way, just showing that. So then I could make brackets that way, but showing we exclude this point. Yeah, so it's everything. So it's 0, that's 1. So how you compare the sets? How many points are there? No, I really don't understand why you are somehow. Of course, they cannot be. Here it's finite. You see, just four elements, just 4, 1, 2, 3, 4, and here we have infinity of points. We also know that this infinity is actually not countable, right? Because the fact that we draw just endpoint, it doesn't change the size, the cardinality. It's still infinite, you see. And of course, finite set cannot ever be equivalent to infinite sets. Right? So infinite sets may be a proposition. And I think it's intuitive, no? That infinite sets are larger than finite sets. And that's it. You see? You only need somehow to unpack the definition of what is power set. And yeah. So the right answer is this, that of course the answer is negative, and sufficient reason, sufficient, yes, proof, if you like, that one is finite and the other is infinite, and that's it. So we don't need even to refer to the fact that it's uncountable. Yeah, okay.
Okay.
Now you see, it's just little trick of professor who wants to ask a very stupid and simple question, but just uses some terminology just somehow to, как сказать, чтобы вас смутить. But you shouldn't. You should resist and see just something very simple behind that question, and that's correct. You see. Okay. No. Okay. Let's next. No. Okay. I remember it because next and maybe finite final exercise is this. We just have two segments, like geometrical. I think I told that already last week, but I think we should repeat many times everything. So I just have two intervals. Let them be different in size, like this. Right. No, let me call it in a standard way, like by the endpoints AB and say CD. And now I should compare set of points, right? Now let me denote it's just AB and CD. And well, let me understand this. I don't know, I don't have any special notation actually for that. I don't think it really exists, but okay, let me just meant that these are, now I think about these A, B, and CD not as intervals, not as really geometrical objects, whatever, but sets of points, right? So I just sets of points, no, meaning points which actually belong here, right? So if this is some X, so X is an element of say AB, and I don't know, some Y here, say, which is element of CD, right? So I look at my of my segments, stride segments, as just sets of points. All right. That's, by the way, conceptually interesting exercise, and in history of mathematics, many times, oh, sorry, starting with Aristotle, there is long discussion about it in Aristotle's physics, for example. But okay, let me leave it aside. And the question is whether these two sets are equivalent or not, or one of these is bigger. No, candidate for being big is CD, right? Because here is, of course, we can establish one-to-one. But what about CD? I think we did this exercise, so try to recall what we told last time about it. Last week, I think. So in order to prove that they're the same size, right, we would need to establish one-to-one correspondence between points of AB and points of CD. And one-to-one, meaning to each point of AB, like X, would correspond just one point of CD, and the other way around. To each point of CD would correspond single point of X. Did you attend last class, people who are now here?
Yes.
But try to, you really forget everything during the week, how it works, because we really did this exercise. So
It's complicated.
no, okay, no, I repeat. So the answer is yes. Yes. So how long we take these segments really does matter. It does matter. It doesn't change this cardinality. And the simple geometric proof for it is the following. We're doing projection, and projection means that I connect A and C, right? I connect B and D. I find the intersection here that let me call O, okay? And then I can do, suppose I have this X here, and now I can project it on CD. right? So I may have kind of an image of X on CD, which is let me call it X prime, right? And I can also describe it. So if let me call this projection like operation by a little p, and that p sends every point of my AB to some point of CD, right? And more specifically, it sends X to X prime, as shown in the picture, right? That's my P. And I also can write it, and you do in school, P of X, like image of X with this P equals X prime. It's all different notation for the same thing. But now observe that actually it also works the other way around. So if I have some Y here, right, basically the same projection, or you can call it inverse projection if you like, standard notation, something like this. It takes this Y, and very similarly, like I projected back, projected back on AB, and so I have inverse reimages, it's called sometime here. So I would call it Y prime, right? So it's actually works the other way around. And now I have Y prime, if I still consider it's from AB to CD, right? So it's, no, I would better put it that way. Y, it project, and this is inverse project. Minus 1, it become 1 prime. And now observe that actually different points on AB always project to different points on CD, and the other way around. Different points on CD project back to different points of AB. So it's indeed one-to-one. Yeah. Here there is something actually that calls for more precision, right? What we really mean by one-to-one, how we're really sure, and that's probably what I have time to tell you. So we still have half an hour, and that'll be new material for today, okay? Because all that was repetition. But if you have questions, better ask me. No? Yeah, but I really urge you to be more serious. Maybe I should send some general letter, because you see the exam is coming, and I don't want you have very bad marks, really. And okay, I would say semester is coming to end, right? So you should really work more seriously. You should look back, and I'll send you exercises of that sort, right? So we've already made 2 tests, and that will be test number 3, and then there'll be 1 more in the very end of semester. But you really need, you see, because you see, now we basically spend the whole time of repeating what was already done last week, and that's okay. I think it's better than not. However, we really need to progress a little bit. Otherwise, we really stick with very, very elementary thing and never have time to. Yes?
Are we going to do next test up to the next class?
Yes, I'll send you.
Okay.
I'll try to send you maybe tomorrow or something, right? So you submit it, and then we, as usual, we look again into this. Okay. Yeah. But please prepare yourself, because you see, it's all relaxed, it's nice, but it's only nice assuming that you really get something, because at the end I need to evaluate you see, and yeah, and if you don't understand something, just ask me, be more active. You see, now it's not situation where I evaluate you, right? So I'm quite ready to answer all your questions, to repeat again, to do anything. You see, so please just ask me. Don't if you somehow lost, just say I'm lost, I don't understand this and that. Okay, yeah, because otherwise it would be much worse, much more difficult to do something. Okay, yeah, no, okay, let me now introduce. We also have introduce complex numbers, but okay, before we go to complex numbers, let me do this, and then I'll come next week to complex numbers. Yeah, so that topic, I think I will give that way, functions and map, right? Functions and maps. Ну, я тоже скажу по-русски, вот это слово map, ну, это часто переводят как карта, да, с английского, но в данном случае это скорее переводится на русский как отображение. Вот если кто-то встречал по-английски глагол to map, something to map. You can also look in dictionary. And to map means отобразить, something like this. You see? So it's not only about map. It's relevant. Now about functions. You certainly came across this notion of function, right? So what is it, if I ask you what is a function, just please tell me. What is a function? I think we had already this discussion, but never mind. Let's have it again. Did you ever heard about functions, or it just you never?
I guess in school.
Yes.
Yeah.
So what was function? What is function in school?
It was 5 years ago. I don't remember.
But I could maybe describe it like a graph that
What?
like a graph that describes the
Like what? Sorry, I didn't.
graph like
A graph,
yes.
like a diagram. Oh, okay, okay. Yeah. No, some other. Yeah, we represented certain functions with graphs. That's or diagrams, right? That's good point. That's good point. Maybe some other hints. This is a good thing. Hint. I'll come to that, right? And what could be some other? No, okay. If there is no hints, let me describe. So we would think about functions in the following way. So first we consider two sets. No, let me call it A and B, right? Sets. And one of these we would call domain, and the other would call codomain. And a function I will represent with an arrow. Then I'll explain how it corresponds to this more familiar notion of function that you learn in school, right? F. Sometimes F is just maybe put in that way, for example, right? Now, what this function does, no, let me use again this kind of stupid geometrical representation. So in this set A, there are certain elements. Well, let me call kind of generic element as a little a, and generic element of B, say little b. Okay. So what that function does, it takes every element actually, right? It somehow works on every element, and it sends each element of domain to certain element of codomain, right? For example, right, it takes this a little element A and sends it to this little b. And that works for every element of domain. That is very important. Sometimes this is written, and that's how you did it in school, I guess, right? In that way. Right. So we put this, yeah, that's also sometimes called an argument. Right. So we take this element, we do something with it, and it transforms into something else, which normal example of function studied in school, they actually almost all or just all, they have of this form, R to R, right? So for example, if you write something f of x equals, I don't know, x squared plus 1, for example, right? That usually means what? That you take certain real number, say, I don't know, 1, or whatever, right? 1/2, right? No, 1/2 is difficult to calculate. Let's say 2. So I put that value here, and I'm doing, I calculate, so it'd be 2 square 4 plus 1, it gives me 5. All right. It's also, why those are real numbers, but not, say, rational numbers, but that's actually related to this two diagrams. And this is because who could actually write a diagram for this function? So this is my x. Yeah, that sometimes it's called y also, right? So if we have 0 here and we have 1 here, it will be a parabola actually, going like this, right? So in if you take x0, its value is 1. So it's that kind of thing, right? Yeah, and why it's important that the real numbers, because only real numbers are continuous. We just discussed with you continuity, right? Being continuous, continuum, right? Because if, of course, you may think about actually the same formula may represent a function from Q to Q in rational number, just meaning you take only rational numbers here, but then you can't really draw this kind of diagram because there is no discontinuity. If you really want that every point is a number and every point of your plane is a pair of numbers, right? Then you need real numbers. It does work with just rational numbers. And of course, you may think about also functions, say, from natural numbers, and not, or say, from natural numbers to, say, rational numbers, right? If I'm writing something of this form, f of n equals, say, n over 2, say, minus 1, right? Then would work well with this domain and codomain. So I take only natural numbers here as argument, but then I divide them by 2. They are no longer rational, right? So I cannot, the result is no longer rational number. So, and even I would have negative numbers here when n is equal 1, right? I would have -1/2. So I need y the codomain. Otherwise, this formula simply does not define a function. You see? So that's, so more generally, again, we have just 2 sets which are, can be the same or can be also different, right? And elements of first set somehow are mapped. Yeah, it's where this, or sent to elements of other sets. And what actually crucial here is the following. Look, it's kind of allowed, of course, that 2 different elements of first set are mapped on the same element of the second set. So we may have situation where, say, A prime is mapped to the same B, right? That is allowed. For example, here, if I take, say, for x, I take 1, I get 2. And if I take -1, I also get 2. So it's all somewhere here, right? You see, we have the same value function for different arguments. However, what is not possible, it's a kind of dual situation where the same element is sent or mapped to 2 different values. So that's a situation is disallowed. No, because otherwise we wouldn't tell what is f of a is, where, so that question where our function really sends our argument, or otherwise in different words, what is the value of this function on that given argument, should really be one unique answer. You see, you can say I don't know, you can say there is no such value, no, and you can say there are actually 2 values, right? So it's one definite value, and that's actually what distinguishes function between among more general kind of conceptual what is general thing, which is called relation, that we'll touch upon a bit later. Okay, so that's how function generally works. So once again, in school you only study function of that form. However, we may consider functions somehow more generally. For example, remember what we talked about logic, remember, and then I may say, if I have something like P, say, conjunction Q, right? That you may think about this again as a function which actually sends pair of basically values. Remember this truth table, right? It only depends what are values of P and Q, and there are only 2 possible values for each. It's truth and false, and this set of true and false, let's call it B. For bool, you can also write 0, 1, but let me write like this, truth and false, for example, right? And then that function, which actually could, here we have a pairs of values, right? And that I denote by cross, meaning that we are interested in values, and it sends, and here I put my conjunction, just to Boolean value. All right, so it's a so I may think about, say, conjunction as a function from pairs of Boolean values, right, of true and false, to just Boolean values, according to our truth table. Yeah, that's just example of function, which is kind of different example, right? It's not about real numbers. It's about something else. So codomain could be truth values, for example, or it could be again something different, right? No, and our examples, of course, were when we considered functions, say n to n, right? Remember when we established it one-to-one correspondence, then f of n equals 2n, yeah, and we actually used it for establishing one-to-one correspondence between n and let me have not n here, are just even numbers, right? As we did. Okay. But now we also wanted somehow backward function, remember? And so we also have this notion, let me go next, of inverse function. Okay. Yeah, how much time? We have 10 minutes left. Okay, let me introduce the remaining time inverse function. Then we kind of skipped some other important notions, surjective, injective, but okay, I'll do it maybe next week already, right? Okay, let's go. So before we talk about inverse function, or say in order to introduce this notion of inverse, the idea is inverse function, of course, that we somehow, so we had a function, say, from A to B, right? And now we can want to go back. Say here we multiplied by 2, and here we want to divide by 2, right? And so it's not simply goes back, but in some special way. So in the sense that if this direction we call f, that we may call f minus 1 that way. Okay. Yeah. Yeah. So in order to really define how it works, inverse function, we need first consider what is a compositional function. So idea of composition is simple. Or I would also talk about maps. So what are maps? Well, let me put it that way. It's something more general than function, meaning that when I talk about function, I talk about sets, right? Like say A and B, what I just said. However, something very similar may work where A and B are not just sets, but say some other kind of structure, say spaces, geometrical spaces, or maybe certain mathematical objects of some other sorts, like graphs, or maybe even numbers, right? So okay, I think I'm not going really explore this, but just keeping in mind that it could be something that these objects, yeah, like domain and codomain, this terminology we actually preserve in all cases. They may be not just bare sets, but something more interesting. And I don't know if we really have some time. I may have time to explain it and give some non-trivial examples, but then you would need to work a little bit more to digest this material, I would say. Right. So, and what I'm going to say about composition, okay, first I would talk about compositional function, and next, maybe next week already, I would talk about composition of maps. Okay, so what is composition of function is a very, yes? Yes?
Oh, I'm sorry.
Okay. Yeah, so suppose you have a function with domain A and codomain B, right? But then you have another function with a domain B and codomain C. Okay, let's call it G. No, and then you see rather naturally, so you map elements of A, elements of B, and then elements of B are mapped to elements of C, and that actually gives you a composition which maps elements of A kind of directly to elements of C. So let me picture it, say that way. Yeah, standard notation, you may expect FG, but actually standard notation is the other way around. Sometimes people put there a little circle like this, right? But the order is reversed. And if I give you some examples, you'll understand very easily why. Let's say, again, this example, I gave you example of this function x squared plus 1, right? But let me now, to cut it into parts, right? So my first function, no, that time we just would say, think about functions from R to R to R. Right? So all this ABC are the same familiar real numbers. And so my first function, f, it takes a number, it squares it. So I can write it in that way, that f of x equals x squared, right? And let my second function, which I can g, but let me now call this variable differently, say y. It's pluses 1, right? It adds 1. So it's just y plus 1. Now, suppose I want to do two things, right? So I square, and then I plus 1. So normally I would write it that way. So I have g of f of x, right? So it's equals g, and now I substitute x squared, right? And that gives me x squared plus 1. My simple example, right? So you see what happened. I first applied f, and I applied my g next, second, right? but if I use this functional notation, I'm writing G on the left. So you see it a little bit like in the case of this decimal or other systematic system notation, right? I actually, to unpack what is going on, I should actually look not from left to right, as we usually read and write, right? But the other way around. So I take X, I apply to X my F, and I apply G next. Even if geometrically I can represent my F goes first, G goes second. You see on this geometrical picture, however, this kind of syntax that we all are familiar with, right? It's actually kind of suggests to write it in the opposite direction. So that's, if you like, a motivation why we're writing it not FG, right? First F, then G, but it is first F, then G, but we are writing it from right to left, not from left to right. Yeah, that's something you certainly did to school. By the way, look what, question, whether or not in that example, that particular example, first observe that not all are compatible, not all functions are composable, right? So in order to compose function, the codomain of first should be the same as domain of the second. Yeah. However, if we have all this domain codomain just the same R, it's always satisfied. But let's look into the order. So that's what we have. We have G circle F, right? But what about if we're trying to compose them in the opposite direction? Would it be the same or not the same if we making that? So that actually means that G is first and F is second. In that example, would it be the same or not the same? Question. Okay, and then we finish. And then I continue already next time. Whether it's the same or not the same, is you square first and add one, or you add one and then you square. Is it the same?
No, it's not.
It's not the same. Yeah, because of course, if you have a G first, you first add one, right? And then you square, you get that. And this is not the same as x squared plus 1. By the way, that's very interesting. If you think about this composition as a operation as something like multiplication, right? Then this phenomenon called non-commutativity. So operation is called commutative if it's always, it works like A cross B is the same as B cross A. And we know that usual addition and multiplication are commutative, right? However, such a thing as compositional functions, it's not commutative. You see, and that is actually very, very interesting phenomenon that we, no, so actually next step that I think I'll do already next week, because I don't want to really be very quick, and we're actually going to use this notion of composition in order to define what is inverse of the given function. Yeah, so next week we'll just start with that notion of inverse. Then we apply this, say, knowledge to talking about. Actually, we may apply it also for proving this generalized version of Cantor's theorem. I'm not sure that you really learned this diagonal argument, but try to look into it again. Yeah, and yes, and then we, I think, yeah, do you know how many weeks it's still available for us? We still have like 4 weeks or maybe 3 weeks.
Let me check.
Huh?
We have 3 weeks, and then we have зачетная неделя from the